Thank you, Safa. First of all, you can see my slides, okay?
Yeah.
Yes.
Okay, perfect. And you can hear me clearly, so which is good. Thank you, and good morning, everybody. Probably good afternoon and evening in some part of the world. I'm not sure, which part of the world you are from, but wherever you are, good morning, afternoon, and evening. And what I'm going to talk about is going to give you, particularly some people who are outside UK, give you a brief introductions of the university where we are and what we do about the renewable energies. And then particular interest I will be talking through is the net zero and the role of solar energy into the buildings. And that's what I will be specifically talking about. Then I will discuss about the particular topic here, which is concentrating photovoltaics and how that is being integrated into the buildings, and what are the recent developments has been done, obviously by our groups and some other groups in the world, and some of the challenges and opportunities we can see, and then I'll conclude. So hopefully, it won't take me more than half an hour or so. So in particularly, the people who are outside UK, obviously this is the map of UK, and if you look at the southwest part, which is this part, that's where the University of Exeter here. So if we zoom here, this part, and essentially University of Exeter here at the city of Exeter, and which has 4 campuses. 2 is in Exeter city itself, and 2 is far to the southwest, near to Falmouth, and this is called our Pendin campus, and 1 campus is in Truro here. And our renewable energy activities is based on the Cornwall campus in the southwest. So clearly, if you are not very familiar with the UK geographically, you can see very much sort of at the end of southwest, if you can see, that's where our campus is based on. And particularly, obviously, I'm a professor at the University of Exeter. I have a role there, permanent role here as a professor and chair in clean technologies, but I also have 2 other jobs, but shall I say, 2 other unpaid jobs, so I don't get paid for it. Which one is adjunct professor in mechanical engineering at Indian Institute of Technology, where I have currently 2 researcher and 1 project is ongoing. And also I've been co-founder and scientific advisor of the spin-out companies we developed about 1.5 years ago from Exeter, which has 3 staff members. But my main job, which is a professor and chair in clean technologies, I lead the solar energy group, which is around 21 researchers, including a couple of academics in the group. And in terms of the renewable energy activities in the department, we have various renewable energy technologies applications and research ongoing. And 2 of the strongest one in the group, in the whole department is, one is solar technologies, obviously, which I lead, and the other one is offshore renewable energies, but also we have power electronics, energy policies, energy storage, and obviously the environment and sustainability in terms of the renewable energies. I think renewable energy in Exeter is one of the first one in the country to established full 4 years undergraduate program. So we have a undergraduate program since 2001, 2002, which has been running very successfully. But that's from the education side, but certainly I think altogether in the renewable energy group, we have about 15 academics and 56, 57 researchers, and something like 150 students in the group as a whole. And as I said, is only a small part, or relatively smaller part is the solar technologies. And particularly in the solar technologies, we do research on the concentrating solar, which I'm going to talk about, the photovoltaic technologies, mainly the upcoming photovoltaic technologies, material for storage. We look into the material aspect from the thermal storage, but mainly related to the solar technologies and how to enhance their solar efficiencies, as well as the building energy efficiencies and so on. So why solar into the building? I think some of you might already been aware that in June 2019, the UK Parliament has passed the legislation to become the net zero by 2050. So that's officially, that's a law. And the law has been, I think, the UK government is one of the first government to implement such law. What does it mean? It means the building, as you know, takes about 40% of energy consumption. So whether building a new house or retrofitting some of the element in the building, as a whole, it consumes about 40% of energy, about the whole sector, about transport, various other sectors and so on. And also, not only that, also the third of the emission is coming from the buildings as a whole, office buildings and residential buildings and so on and so forth. So there is a huge push of the energy efficiency for the building sector. And the Industrial Strategy Boards, it's found a few years ago by the government, has target by 2030, half of the energies in the new buildings need to be halved. And not only that, and the zero emissions is going to be, it's a mandatory and has to be zero emissions by 2050. So there is a huge target, and not only we can just replace the whole buildings, but energy efficiency is one factor within the building materials, but how we can have much better net zero element into the building. So meaning that, I mean, if we look at a typical building's energy consumptions, there are obviously various factors, water heating, cooling, lighting, space heating, and so on. Obviously, a lot of the glazing unit is being improved from single glaze to double glaze to triple glaze now, and advanced glazing. But even though there are some inherent parameters which we can't deal with unless we have a better efficient materials. For example, losses from the roof or losses from the walls and grounds, windows, and so on. But in contrast, what we have is freely available solar energy, which we can tap within the building environment on its own, and then make a use of it to become net zero. And that's the area of line I'm going to talk about. So why the solar in buildings? Obviously, there are many benefits. I'm not going to go through in detail, but obviously the solar PV, one of the main thing, the photovoltaics, mainly for the electricity power generation, is we don't need to have a multi-megawatt or gigawatts of solar panels somewhere at the desert and then bringing the power to the user. I mean, instead, what we can have is we can have the the electrical power generation at the point where it's needed. Meaning that if we are talking about a particular building site, then the photovoltaics or the solar panels, what I mean by solar panels is the solar electric panels or the photovoltaic technologies can be in the buildings and then used to the at that point of uses. So I think which is extremely helpful in terms of the power losses and also from the sustainability point of view. So there are many other benefits, but typically the photovoltaics goes into the buildings in two ways. One is called building integrated photovoltaics, or where we can replace an element of the materials for the building to have a solar modified panels. Or another way is the photovoltaic panel which goes on top of the roof and add an adjacent material, meaning that as an additional element of the component. So in the first one is essentially we are replacing the material. So remove the building materials, apply the solar materials into the buildings as a component, which has a different challenges as opposed to the building or PV technologies which goes onto the roof. And I will give you some examples of the BIPV technologies or building integrated. As you can see here, the whole facade supposed to be in the glass facade. Instead of having the glass facade, glass is replaced by semi-transparent photovoltaic technology. So that's, obviously we are not only replacing the glass, but using the power generator at that point of time. As you can see here, another type of semi-transparent photovoltaics is skylighting. Again, in the similar concept, instead of the fully glass, you may not need large amount of sunshine. Essentially, you can tap some of the electricity and also get the daylighting into the building. Wall curtain is another type. Tiles, photovoltaic tiles. There are companies now working on or manufacturing the solar tiles so that instead of having the roof tiles, we can have the PV tiles. And what we are doing here, we are replacing the building materials as a PV generator. So that's what is called the building integrated photovoltaics, as well as the windows and so on. The major challenges in building integrated photovoltaics is efficiency is the big challenge. The cost is the, obviously, we are not comparing the cost of a standard photovoltaic panels, because obviously, standard photovoltaic panels has a quite low cost these days because of different technological evaluations. The cost has been reduced significantly, but where the glass and glass PV panel mainly applied for the BIPV technology still has a higher cost. But the main challenges here is light transmissions. So mainly, I mean, if, as I said, if we look at the sky lighting or wall curtain, what we need to be making sure that the light is going through into the building as well as generating the electricity. So there is a balance with that. And not only that, the U values or the G values, the solar gain values into the environments that need to be quite optimized, which is related to the heating of the element. So why concentrated photovoltaics? Why not standard photovoltaics? As we know, The concentrated photovoltaics typically use optical chip optical materials, focusing the sunlight to the solar cell. And then depending on the technologies, we need a heating or cooling, cooling as a heat sink and so on. The main reason here is obviously the efficiency of the solar cells is very high. But not only that, because of the uses, the semiconductor materials we are using here can be quite reduced quite significantly. So typically the concentrating photovoltaics is a combination of an optical device, the solar cells, and a heat sink. So why concentrated photovoltaics? The world highest efficiency been developed last year, 47.1%. It's a very small size, like 5 millimeter by 5 millimeter cells at NREL, National Renewable Energy Laboratory in the US, developed 47.1% efficiency. So when we compare the efficiency with the dollar per kilowatt hour, is quite significantly low. And not only that, and the material availability and the issues related to the recycling and obviously silicon recyclable and so on is quite challenging. So all these benefits, when we use all these criteria, the CPV or concentrating photovoltaics has a slightly much better advantages. However, having said that, though, there are a lot of challenges, and the challenges are the tracking required, moving the device to the focusing sun, which is really limited in case of the building application. So in that sense, there are certain technologies, I'll come to that in a minute, how we can integrate into the building, and I'll discuss about the research which is ongoing. So in terms of the concentrating photovoltaics, as you can see here, in every single photovoltaic technologies, yearly efficiency published by NREL, National Renewable Energy Laboratory, which clearly shows the 47.1% about a year and year or more ago, developed by NREL, which is 47.1% PV efficiency as compared to the silicon technologies, which is 23-24%. However, having said that, very recently, last few years, another technology called Perovskite solar cells is really kicking off quite high pace, and the rate of increasing efficiency is significantly higher at present time. So when we are talking about concentrated photovoltaics, there are two parameters called the geometrical ratios and optical ratios, and depending on the ratios or the what he called the aperture, where the light is focusing to where the light is going, depending on that, one can divide into the three different categories: less than 10, which does not require tracking, and which requires one axis tracking here, and this is very much more than 100, which is required two axis tracking. So the main technologies we are working is less than 10, because we don't need a tracking, and it can be incorporated into the building quite positively. And what do we use? We use lens, we use mirrors, and we use also total internal reflector materials, meaning that there is a dielectric materials or particular PMMA or glass-like material which taps the light and refocuses to the solar cells at this point of time. And giving that what it does, it allows some of the light passing through the building envelope, and some of the light is being captured and re-diverted into the solar cells here, meaning that instead of having a solar cells from here to here, all this area, we are using only a fraction of the solar cells, but then allowing some part of the light to go into the building. Because what we don't want in these particular technologies, as I said, in the BIPV technologies, is cover up the whole area with photovoltaic materials and then turn on the lights inside the building's envelope. So the applications is mainly for example, facades, skylighting, curtain walls, conservatories, and so on. Whereas the other type of photovoltaics which goes into the roof, that is a completely different area of interest. And typically, the research is ongoing in our lab in all these three areas. We can say CPV for the buildings is a building integrated concentrated photovoltaics. As you can see the picture here, clearly, I mean, obviously, you know, if you ignore this part, but still this part here, you can see some of the light coming through and also generate some electricity. Also, the building applied concentrated photovoltaics, which goes onto the roof as a where daylighting is not important issues, for example, and if it is a glass roof, for example, or some other spaces where daylighting is not really an important factor, we can have much more dense array of PVs and CPVs getting a better efficiencies and so on this one. And the third one, we, as I said, we have developed the spin-out companies, and which we came across a particular type of PVs related to the photovoltaic, related to the construction material, meaning that if you have a large glass block, for example, this particular picture you see, it's a it's a drawing essentially. I mean, and this drawing is for the St. Pancras railway stations. We are engaging with the National Rail. I mean, particularly from the Build Solar, the companies, spin-out companies, engaging with the National Rail to implement such technologies. And as you can see here, where the public interest is there. So essentially, meaning that if you have a large amount of PVs on the wall, that's no good use, because you don't get that any daylighting at all inside. Instead, what we are using, that replacing that whole glass block to use the PV or photovoltaic materials inside the glass block, so you don't see it from outside, but it generates some electricity, which is called the Build Solar Daylight or Build Solar Max, two different products we have generated from the spin-out companies. So main component of the BIPV, BICPV technologies are obviously the glass is large, component, the optical materials, and the solar cells. Obviously, I mean, this system does not require tracking. As I said, it is for the building integration. So we cannot just move the system focusing the sun. No complex fins are required, meaning that heat issues is really less significant and used for the building integration. That's where the technology is. And one of the first systems we developed back in 2003 when I was doing my PhD, as a reflective optics. As you can see, this one was in Northern Ireland, picture taken in 2002. And the paper was published in 2003, looking at the reflector materials for these type of applications where we gain quite a significantly high power ratios. However, having said that, there are some issues, mainly particularly because of the optical materials that absorb the lower frequency sunlight or lower wavelength sunlight, meaning there is a losses in the 380 to 400 nanometer wavelength range. That has been modified with the better glasses and the protective coatings on top of the glass, but that is one of the first reported data in this area one can find. There on, as you can see here in the picture here, when it's exposed indoor sunlight and the outdoor, we have a very good power ratio. That means essentially we get about 2.25 times of the power factor as compared to the solar cells without the optics. Then as opposed to the linear system, then we moved on to the more complex device using the three-dimensional optics, different profiles. So we looked into it, different range of concentration ratios. We looked into it, and obviously that involves very complex mathematical formulations. Obviously, I mean, I'm not going to go through it, and which generated not only a few publications, but also a patent in that point of time, which led us to develop this novel BICPV system, which essentially consists of the solar cells, some optics, some glasses in between, and encapsulation material, and so on. The picture on the right, you see there are various different versions of that. This is one simple version of how can we maximize the sunlight capture throughout the whole day in a particular location. And not only we use the polymer materials, but also we use the glass materials, essentially showing the concept being used. Also with my my collaborator in the country and outside, we develop a different type of optical concentrator. As you can see here, is mirrored symmetric concentrator, which essentially collect more sunlight throughout the day, and there is a significant amount of both optical flux requirement and a light trapping mechanism and so on. So for the sake of time, I mean, I'll just move quickly and see what are the opportunities lies. And in terms of the main research, what is going on, we are looking into the next generations of optical device, particularly from the reflective side. Just a couple of years ago, we published an article in Nature Scientific Report looking into how to use the nature, for example, in this specific case, butterflies and their wings, and what do we understand from these particular type of wings to create reflective materials, which has a power to weight ratio is 17 times. That means if we create these materials as an optical device, we get almost 17 times power more than the weight ratios. And as you know, the weight is being a significant factor for the building integrations and so on. They fly quite faster, and they take off quite significantly shorter time as compared to their competitors. And as a result, what has happened, their wings has a certain degree of natural combinations which reflect some of the lights. As you can see here, we have measured, taken the butterfly wings and taking their reflectivity maps, and then trying to create the materials. And we have just communicated one article on the materials we have developed from these concepts. Also, onto the biomimicking side, one of our students has recently developed some optical methods for creating the moth's eyes to capture more sunlight, and we are just going through that particular articles in coming days. Another problem is the main challenges is how we can use both the refractive and reflective optics, meaning that where we have the reflections and where we have the refractions. For example, the total internal reflections, how we can combine them together to have a minimum losses. And there are some articles in this area also to have a better efficiencies the solar panels and removing, for example, some of the lights, as you can see here in this part, is escaping from the system. So how we can trap those, there is a combination of these two optics involved. And very recently, with the development of perovskite solar cells, perovskite solar cell has a huge potential, as I said, in terms of their the possibly cost reductions, and the key information here is how to make a larger device and the stability is high. So in sustainable energy and fuels, we have published last year, I think this is one of the first type of the device that integrating the optical, low concentrated optical device, as you can see here, with the EPFL in Switzerland, who manufactured the cells, and we manufactured the optics to integrate in the low low concentrated optics, which has given 21.6% efficiency. But the interesting thing is we achieved a perovskite solar cells, which is like 9 millimeters squared as opposed to the perovskite on its own. So left-hand side, what you see is about 3 millimeters squared, and the right-hand side, you get a power factor of 9 millimeters square. So it's quite a step change happens in that front. And as you know, I think the problem in perovskite is scaling up is a huge problem. Although the stability is low, about 5 hours, but this is quite a significant development. And this particular article, it came to the front page of the journal Solar Fuel, Sustainable Fuels. And what you see here in these two pictures is without the optics and with the optics, said that there are significant challenges with the stabilities, with the efficiencies, with the much better fill factor, and we are constantly working on these areas. And the last one is when we have a BICPV system or building integrated concentrated photovoltaic systems. In addition to this, how we can control the daylighting by using some smart glazing on top. And this is one recent article we published again, using polymer dispersed liquid crystals on top, so that it has a enhanced performances. And ultimately, what we see is building to be a power generator. That means building on its own requirement, which essentially needs the modeling, electrical device modeling, spectral modeling, heat transfer modeling, optics, as well as the system development and so on. And with that note, I wanted to conclude that obviously building integrated concentrated photovoltaics has a lot of challenges, but the main benefit of what we have is the electricity generation at the point, the light transmissions, and possibly reducing overall heat loss coefficient, and such systems need further investigation in terms of the research and development. And I want to acknowledge, obviously, Professor Safa Rifat for inviting me to give the presentations, and the society. All the funding agencies, obviously, I'm associated with, and all the past and present researcher and collaborators and so on, and obviously my group members, without whom I won't be able to do any of the work. And thank you for listening. And I'm very happy to answer any questions I have, if you have.
Thank you very much for your very interesting talk. Colleagues, do you have any questions for Tapas?
Yes, I have a question. Tapas, is a very good presentation, by the way. And you mentioned about the perovskite sources applications, and with the integration of your concentrators lens with the EPFL constructed device. My question is the stability. You mentioned 5 hours of stability, if I'm not wrong. What do you think in terms of the feature? Would that be able to handle the concentrated solar radiations for 24 hours in a hot, arid climate?
Yeah, that's an extremely very good question. I mean, couple of things I need to give you the background of it. I mean, perovskite solar cells only been developed since 2010, so it's less than 10 years old as a technology, as compared to silicon technology, which is much matured and better stable cells. They are been developed since 1950s. The research and development is ongoing. But if you look at the pace, perovskite is moving extremely fast than the perovskite, the silicons or any other solar technologies is been happening. Yeah. So the rate of change of stability increase over time is extremely fast in perovskite than any other solar technologies. So that is one point. The second point is the type of optics. As I said in my talk, we are using low concentrators, what is meaning that we are not using very high flux solar radiation, but we are increasing the areas significantly 2-3 times higher. So therefore, these solar this data I have given, this is I think to the best of my knowledge, this is first ever studies been done on the perovskite and been reported. So obviously, over time, with the improvement of the understanding, much better understanding of the solar cells itself and the integration mechanism, I have a strong feeling that over a period of time, it will achieve this, at least some degree of stabilities in the days to come.
Sure. Thank you, Tapas. Much appreciated.
Any other question? One more because time. Any other questions?
Yes, I have a question.
Yeah, please.
Hello, Malik.
Hello.
Hi, I'm Gui Chang. Nice to meet you.
Hi.
Yeah, I have a question. Could you please predict the future development of concentrating PV in buildings, or why the buildings may choose the CPV?
Yeah, that's another very good question is, but as I said is, I think, I mean, we have to be slightly careful that when we talked about the CPV, we don't talk about from the building aspect, just a standard CPV, which is you will see a big lens and big mirrors and so on and so forth. What I have spoken about is, I think, the main uses of the building aspect is the how it goes into the, for example, this construction material. So building as a integral part of the CPVs into the building fabric, for example, for the use of conservatories, for the use of facades, for the use of skylighting. I think there is a potential market, and this the spin-out companies what we created, Build Solar, is currently engaging. We have a project from Innovate UK to work with National Rail and HS2 to develop a first ever demonstrations in Reading stations. We are working on that. So hopefully, I mean, we will see more on those. And what, as I said, is what I can see is there is a large future in these particular type of applications where the building can be acting as a power generator rather than just a photovoltaic installer, if you like.